Okay, so let's get going. Today we're going to talk about optimization for deep networks. Just first of all, reviewing what we did from last time. Quiet, please. So we talked about the decomposition of the loss for a typical predictive model. And we said that it breaks down into a bias term and a variance term. And this graphic shows you sort of an intuitive picture of what bias and variance look like. The idea is, if you're estimating a prediction at a point X, so a fixed point, the prediction is also a point. And if you have low bias and variance, the ideal value would be the center of the target. If you have bias, then all of the predictions are systematically away from that ideal. So that's the bottom left. If you have high variance without bias, then the predictions would be scattered around the right answer. And if you have bias and variance, then they're both offset and scattered. So anyway, bias is the expected difference between the predictor. So it's an actual sort of vector in whatever output space you're in. So the difference between the prediction, let's see, the actual prediction and the average of the actual output and the value of the predictors. And variance is typically a squared distance. If it's a vector, it would actually be a distance. So the squared error, if it's an L2 loss, breaks down as the square of the bias and the variance. And typically improving one tends to drive the other one up and vice versa. And roughly speaking, you want to have bias squared and variance having approximately the same magnitude. So one way to reduce variance, we argued, is to incorporate regularization. And we showed that you can implement that effectively with a prior on the weights of the model. You make an entire probabilistic interpretation of the min square, least squares problem as a Gaussian estimation problem, a generative model. And then it adds this additional term in the loss. And minimizing that additional term tends to shrink the weights a little bit. It's increasing bias, but it's reducing variance. Improves the condition number of the matrix that you need to invert. So the more the regularization, meaning the larger the lambda parameter, reduces variance, but also is increasing bias. And vice versa, if we use a small regularizing parameter, you get more variance like the original model without regularization, but you should have reduced bias. So last time we also talked about hinge loss, which is the basis of a support vector machine. And here's the graphic again that we had last time. So there's a blue curve which represents the loss for the black points, and the red curve represents loss of the white points. And the loss starts increasing as soon as a point crosses the margin. So there's no loss when you're outside of the margin, but in that middle region between the two dashed lines, points are inside of their respective margins, and so there's loss in both sides. But anyway, the effect of this, the increasing loss, since you're minimizing loss, the gradients will tend to push this boundary between the two point sets around such that it's trying to maximize the distance from the points, which will minimize the loss. So an SVM creates or tries to create this margin between the points on the two sides of the boundary. We also generalize from two-class classification to k-class classification. And this is the formula for softmax, which generalizes the logistic regression formula. And we argued that if you use a cross-entropy loss, which is a natural loss when it's interpreted as a probability, as a label probability, then minimizing that, substituting into the expression you show that actually gives you this kind of soft hinge loss. so that the logistic classifier also behaves as a margin classifier. So the assignment, first assignment is out and it's due on Monday, February 17th. As soon as you can, make sure your configuration's working and you can load the appropriate dependencies or run the virtual machine. Starting from now and especially next lecture, we do back propagation. So you should have all the tools to do the assignment as we go along. My favorite topic. So there'll inevitably be some issues when you're doing the assignment. We want to have you get up to speed and solve those issues as quickly as possible. So it's very important, probably more important than you would imagine, to follow a structured error reporting process when you're doing that. So we have a page up expressly for that purpose, and it's drawing on best practices in industry and other sources for how to report bugs. Reporting bugs or issues is harder than you think. You want to give as much information as possible, basically. So certainly including the system, operating system, software version for all the relevant software that you might be using. Very explicit description of what happened, not just the name of the error message, ideally screenshots or at least the full text of a text message. Also what you expected to happen. Because sometimes people look at bug message and say, well, that's fine. Because the person that sent the message didn't really explain what they expected to see. And an issue is really a difference between what you expect and what you see. But sometimes people don't know what you expect, and they may not know why you're troubled by what you saw. So you should say explicitly what you expect, and contrast with what you saw in the message. And as much as possible, right, someone else is seeing this, they may be able to figure out what happened just from the error message. Often they won't be able to. They may be puzzled why that error message came up. And in terms of diagnosing, they may want to try various things, which means they have to reproduce the problem first on their own machine. So, and it may be that you skipped a step or you did something wrong. So saying exactly what you did is necessary for somebody debugging to figure that out. So you should say what you did, not I followed these directions, because 9 times out of 10 when people say they followed those directions, they didn't. So actually say what you did. The directions may not be very good, and there's often vagueness, and that can lead people to do the wrong thing. And many companies actually have some kind of form or format for issue reporting, so you might as well get used to being very explicit with what you say. And it's very important. Well, it's important here because you want to have a good relationship with us. We're the staff. We end up helping you with problems and also grading things. So you want to have a good relationship with us, so the more that you can make our job easier, the better. The same with system people or support staff in industry, if you're in an industry job. Empirically, from our experience, it's 2 to 5 times quicker to solve problems if somebody is very explicit in reporting them and follows the steps. Most of our time ends up debugging problems where people didn't follow the steps, so that's frustrating. Most simple issues, if you give enough information, somebody can often just eyeball and say, I see what's wrong, and solve the thing in one transaction. Don't just assume that hashing works. That is, maybe you see an error message that looks unusual, and that should specify what the problem is. Often they don't. Occasionally they do, but many common problems lead to strange-looking error messages. So don't rely on that. And the reason people get into most trouble is that there's a tunnel vision phenomenon, which is that the reason people get stuck, can't solve a problem usually, is that they're assuming that they know what the problem is, and they're not right, but they keep trying solutions based on their assumption of what's wrong, like the, I don't know, it's some NumPy array is the wrong dimension. It might be something completely different, and the reason you got stuck is that you had a wrong assumption about what was wrong. So if you don't give all the relevant information to the person trying to diagnose things, they're stuck with the same tunnel vision that you have. Even though they don't have tunnel vision, they would like to know more, but you're only giving them what you think is the problem solution. So anyway, so these things will help on the reporting side, and we certainly encourage all of you to help each other out. But the best way to respond to issue reports is to help the poster figure out themselves what's wrong. So if you can also tell them, all right, well, try this, or it looks to be this, go ahead and try this solution. Or it may be, let's say, I don't know, it may be a mistyped object, so go and check the types, inspect the types of the objects being passed around. The more you can sort of push the diagnostic process, your own diagnostic process, to the original poster, the more they're, it'll help them next time to solve problems. Any questions about this, by the way? Or any thoughts? So cool, so please do this. It'll make everybody's life easier. We can save a lot of time if we all follow this set of principles. All right, so the main topic today is optimization. So we're interested in training deep networks on minimizing some loss. There are very, very many parameters. Surprisingly, we can use simple methods to optimize, but still there's some tricks, so we want to talk about that today. This is an actual deep learning neural network loss landscape, and our goal is to minimize the loss, so to get to that one looks like a global optimum. At the very least, we want to get to a good local optimum, local minimum. And the X and Y are the parameters. Often there's always more than that, but loss is the Z-axis. So naively, we could sort of move around randomly and take the lowest point. Why isn't that very good? Well, among other things, there's a curse of dimensionality here, meaning the space is enormously large. And if you think of even trying to build a hypercube, the number of points in a hypercube with just 2 measurements in each coordinate, it's like 2 to the dimension. So it could be 2 to the many thousands. So we can't ever hope to have any kind of reasonable coverage of the space. Although there are gradient-free optimizations, what they basically do is examine a bunch of points. Luckily, it does turn out that the gradient typically has a few strong coordinates, and it's enough to estimate that from a small number of points. Anyway, for the most part, we won't be doing this, but it's not actually totally crazy. And it's used in some recent work. It does have the advantage that you can use a lot of parallelism. We'll instead use gradient-based methods. We'll see that in a moment, though, that there's some tricks to do that. So in terms of losses that we've seen so far, we've looked at least squares loss for linear predictors. We looked at hinge loss for support vector machines, which gives us a margin. And we also observed that the cross-entropy loss applied to a logistic or softmax prediction is an asymptotic hinge, right? So it approaches 0 for negative S and approaches S for a positive S. So in fact, that's also a margin classifier, and it's also differentiable. So they're pretty well behaved anyway. So we can compute derivatives and backpropagate, which we'll define soon. So going back to gradient-based methods, here's a picture of a surface with 2 parameters, and then the value of the function is the z coordinate. The gradient is a vector of partial derivatives of the loss function with respect to the weights. Yeah, so that's how the function changes with a change only in one coordinate with the other coordinates fixed. Yeah, so the gradient vectors are down in this xy plot shown in red as arrows, and the blue is the surface. So when the gradient is 0, basically that means it's a location where all of the red vectors are 0, and that means that the function is not changing in any direction. Okay. Slightly different version. All right, never mind. So we're ideally going to find a local minimum of loss. So we want to move in the negative gradient direction. So to be more concrete, if we have a set of weights, which we'll just represent as a giant vector, then the weights at iteration t plus 1 equal the weights at iteration t minus some learning rate alpha times the gradient of the loss with respect to the weights. So in other words, we're following the arrows. We're kind of doing a flow of small steps following the arrows. In fact, well, I said that a bit sloppily. We're following, in fact, against the arrows, so the reverse direction, because there's a minus sign there. Because the arrows, are pointing in the direction that the function increases. We want to go to an optimum of decrease by decreasing, so we go in the opposite direction of the arrows. All right, so far so good? Okay. All right, well, let's quickly review this. So the gradient vanishes at local maxima, local minima, saddle points, or all of the above. Who thinks just B? All right, no one, all right, okay. Who thinks just C? No one, all right, well, presumably, okay, so it's not local maxima because although there are some maxima there, they're actually at the corners. That's not the only place. Come on. In this plot anyway, there's a single local minimum, which is in the center of the grid. And there are actually some saddle points right on the edge of the plot again. So yeah, I don't know if how well you can see it, but just in the middle of each edge of the graph down below, there's the gradient's vanishing. So those are saddle points. But in fact, all of them are minima, or all of them are, zeros of the gradient, okay? It's not super easy to see, but you can kind of see the vectors getting quite small in those areas. All right, now the saddle points. I did mention this very briefly last time. The saddle points are a big problem. If you can imagine this plot. Well, we already said that the gradient descent method is going to kind of flow along the arrows. And it's also going to flow at the speed of the arrows, because the steps that we're taking are basically gradient steps. So when the arrows get very small, we're taking very small steps. So you imagine sort of traveling down, let me use the mouse here. If you imagine that we're traveling down this surface here, which would be, let's see, coming down here, we're going against the arrows, but the arrows get very slow in here. So we would eventually come out, we'd safely exit going down, but it may take us a long time because these are the flow lines, and they can approach, as they approach the center, they get slower and slower. So if I'm really unlucky, I might come right down the middle here, and even though it's not a local optimum, I essentially can get stuck on this unstable right in the middle of the saddle. But even if I go close to that, I'm spending a lot more time in the saddle point trying to take small gradient steps than I would be somewhere else. So that's bad. And let's go. Yeah, gradient small in there. So we make slow progress going through there. And so the reason that is really bad is for sort of various arguments you can make. A very intuitive one is that the curvature of a surface at a gradient 0, you can determine it from the Hessian matrix, which is the matrix of second derivatives. And basically, the eigenvalues are the curvatures of that saddle. And those eigenvalues can be either positive or negative. If they're positive, you're at a minimum in that direction. And at a local minimum, you have to be positive in every direction, right? In other words, you're always at a bowl like this and not a bowl like that. At a saddle, you have a mixture. Some directions you're at a local minimum, some you're at a local maximum. And if you think of those eigenvalues as being somewhat independent of each other, a minimum is you have to have some large number of eigenvalues, let's say 1,000 of them, all with the same sign, all positive or all negative. And the odds of that, if you think of tossing a coin to get the eigenvalue direction, are astronomically small. So in practice, maybe it's not quite that bad, but it can be pretty bad. So there are a lot of these on average compared to the local minima and local maxima. All right, let's see. Okay, so yeah, there are some things that you can do about that. Empirically, though, people still just rely on simple gradient following methods most of the time and live with the fact that it can take a very long time for things to converge. There are smarter methods that try to recognize when you're near a saddle and add some noise to get around it, but it happens so often that it's very expensive to do the detection, and it's often not worth the trouble. So most of the world is still using simple stochastic gradient descent. So yeah, so if we have a loss function that's defined on our training data set, when we talk about gradient methods, we're talking about minimizing the entire loss, which means taking the gradient of the entire loss on all of the data points. Luckily, it's linear, so that's just the sum of the losses for each individual point. But still, that's a full pass through the data set. For ImageNet, that's about 1 million images. That's an awful lot of work to take one of these tiny steps. And for deep learning, people almost never use classical gradient descent, which would compute gradients on the entire data set. The method that works incredibly well, in many ways much better than doing that actually, is to use a mini batch of data. So you pick a size, usually a power of 2, works well because of memory limits, GPU, threading structure. So it's typically 32, 64, etc. So you take a block of data samples of that size from your full training data set. Should be random. So one way is to sort of shuffle the data so that it's not really a random sample, but at least you're eliminating possible correlations in the input data. And then you take this small set of samples, and the notation of the sum is just expressing the fact that that the actual sample number is from a subset of size 32, size mini batch from the full training data set, and lies in the range 1 to n, which is the total number of samples. Okay, so you sum over that mini batch the gradients, and that gives you a gradient step t. You do the full update as though you had a true gradient, and then you continue. So one quick observation is if we take random samples of the samples, then because everything is linear, this gradient here is this expected value. It's the same as the true gradient. Is that clear? So if I compute, if I compute an average on a subset of values, its expected value is the same as the average of all of the values. Okay. So it's what's the word? Reassuring that doing things this way, at least I'm taking steps that are the same on average as doing a full data set step. So really the notation looks the same as before, except in my mind I'm remembering that gradient GT is computed on a mini batch. Okay, so now if M is the mini batch size and capital N is the data set size, in a single pass through the data set, now I'm computing that many updates because I'm doing it in batches of M. And in practice, if I have 1 million samples, like for ImageNet, if I'm doing them in batches of 32, then that's about 32,000 updates for one pass over the data set. Yeah, question?
If we're doing batch gradient descent, do we...
You mean full batch? Or
full batch.
Yeah.
Are we going to divide the sum of the gradients by the number of training samples?
In practice, it's a good idea because otherwise the gradient is sort of arbitrarily scaled. There is a bit of difference in implementations of that, though. You have to. And there are, yeah. It's always worth checking and figuring out what your toolkit does.
Okay.
For a lot of reasons, most mini-batch methods use an average, but not all of them do. And generally, if you don't do it on the whole batch of data, it's probably scaled. It's much too big. Yeah?
From an ideal perspective, it says that we random sample. Would that be random sample with or without replacement?
So it depends on on which paper you're looking at. Some of them assume with replacement. It's simple. Usually it's much simpler to do analysis with replacement because then there's no dependency between the samples. So most of the papers that analyze SGD assume that it's with a replacement. On the other hand, it's pretty close when it's without replacement as well. When without replacement is what you're really doing if you're making a pass over the data set when it's shuffled. So it's typically, because the size of mini batch is typically much smaller than the size of the data set, the actual difference is typically small. So this is called stochastic gradient descent, and it's still, with some slight tweaks, the method that's almost always used. So, and as we noticed, it's just the average gradient of a subset of samples, so it's the same in expected value as the average gradient of the whole data set. In other words, it's an unbiased estimate of the full gradient, but it'll have a lot more variance, right? You compute on a different mini batch, the gradient will be different. So that's called, well, that is the stochastic component, stochastic or random component, and it's just an estimator instead of the true value. So this shows a contour plot of a loss function. Is everyone clear on what that means? So these are levels, different levels of different values of the loss, and let's assume that's a minimum. So the lowest loss is the ellipse that's just outside the point, and as you go outside from there, the loss is going up, and it's equal along a contour. And when you have a contour like that, the gradient is at right angles to the contour, because that's, if you have a constant value one way, the steepest direction must be orthogonal to that. If you think about a plane anyway, it's kind of obvious. So the gradient point's orthogonal to the contour line, and that's the direction you would get if you computed the gradient across the full data set. But if you compute on a mini batch, then you'll get some stochastic variation. So it'll be, your vectors will be close to the blue vector, but not quite the same. But the idea is that if you, even with that little bit of noise, you make reasonable progress on average. Obviously, you want the noise in magnitude to be smaller. Should be a bit careful. I mean, it's obvious if the noise is quite small compared to the signal, which is the blue arrow, then this should work. You make progress on average towards the minimum. In fact, the noise can even be a little bit bigger than the signal, and it will still work with a little bit lower learning rate. So, but you do use the fact that your data sets are large, and so taking many, many steps, even when they're individually quite noisy makes good progress. Okay. So if you've had an convex optimization or an optimization course, though, you'd still probably say that might work, but it's awful because it's making such inefficient steps. Why don't we just, you can see geometrically that the gradient itself isn't really going the way you want to go, right? You're going normal to the surface, it's actually very far from the optimum. Is that clear? So you really want to go straight towards the optimum. So if you had some optimization, what would you do here? Yeah?
Well, a Newton's method or something that takes in the second.
Yeah, second derivatives. Newton's, yeah, basically you analyze the curvature of the surface, or if you want to think of it another way, you can kind of scale the plot so that it's circular. When it's circular, the blue vector is the right direction. And they're all related ways of doing the same thing. So yes, Newton's method. There he is. And we'll see him again soon. So Newton's method, you can derive using a Taylor series. The idea is look at this expansion around a point x. You take a step of h away from x, and you can expand that on the second line there. And if we want to find a zero, okay, basically we ignore this term and just solve for h from this equation. Is that making sense? And we approximate f of x plus h as f of x. Interestingly, we'll relax that in a little while. But does everybody see that by rearranging this and essentially letting h go to 0 in the estimation of f, we get this term. Is that okay? Yeah. So let's see. So the h, yeah. So that's the step, and basically we say that t plus 1 is xt plus h. So we add the little offset h to x, and that should do a better approximation of being 0 than the previous one. So this xt should be closer to 0 because it's approximating x plus h. All right, so this is giving us, by the way, notice this is giving us an approximate 0 of f, but we want to actually find minima of f. So that just means that we want the 0 of the gradient, or the derivative of f, okay? So all we do is instead of f, we use f prime for, okay, so for zeros of fx, yeah, that's the formula. If we want instead a 0 of f prime, of the derivative of f, then it's just the second formula there. So we just take the derivatives of f and f prime, and we get first and second derivatives. And so now you can see it's explicitly the derivative value divided by the curvature value. So we're, the curvature, the inverse curvature is an estimate of how far you want to move to change the gradient by from that value to 0. So because it's based on kind of zeroing out curvature, if you have a function f that's already quadratic, it goes immediately to the optimum, or at least to a stationary point. Even with errors, though, even if it doesn't go straight to the optimum, the gap between that and the optimum is smaller. It's has quadratic convergence compared to first-order methods which have linear convergence. So you'll see it going to 0 very fast. So if we're in multiple dimensions, in high dimensions, we want to get to a 0 of the gradient now. You can still Taylor expand a vector formula. So now x and h, though, now they're both high dimensional. But the Taylor expansion looks like that, where H, this is a little, no, that's fine, sorry. Capital H is the Hessian. Capital H sub S, which is the matrix of second derivatives, which we'll put up in a moment. So it's just generalizing Newton's original formulation to multiple variables. And again, we ignore the H term, and we assume that f of x is well approximated by f of x plus h, I think. And we get this expression down here. So now we're updating x by a vector h. And the vector h is given by that term on the right side there, this one here. And so that's the second order vector Newton's update. And the Hessian matrix, now it's like a curvature, so it's a second derivative. But because we have a vector parameterization, now taking second derivatives, you've got to consider all pairs of directions. So the representation of that is a matrix. And the diagonal terms are actual curvatures. The off-diagonal terms are sort of cross terms, cross curvatures. Okay. Now, just a small caution with Hessians is that they're sometimes written in that form, sometimes transposed. Actually, I guess it doesn't matter, does it? Never mind. Doesn't matter. Okay, so yeah, so we would like to do this Newton gradient step. We just argued that you could do a Newton step, but there's some very strong reasons why people almost never do this with deep networks. So okay, yeah, so it would converge very fast on a convex optimization problem, but in practice it doesn't do very well in deep learning. So why do you think that is? Yeah?
You have no hard guarantee of complexity with whatever data set you're using.
What do you mean by complexity, though?
Sorry, convexity.
Convexity, yes.
Convexity.
Yes, so yeah, we'll get to that in a moment. So it'll get you probably to a gradient 0, but that probably won't be an optimum. Yeah, yeah.
We just argued that there were too many saddle points, so wouldn't it just get stuck in a saddle point?
Yeah, so all right, that's the key reason. So if you think about it, the stochastic gradient descent, by simply following gradients, it flirts with saddle points. Like it might accidentally go very close to a saddle point and take a long time. Newton's method zeroes in on the saddle points and goes right there, which is the worst possible thing you could do, right? Instead of going really slowly, you don't go. So a couple of other reasons, though. It's also very expensive compared to stochastic gradient. Stochastic gradient only has linear complexity in the, because there's, it's a vector of first derivatives. So there's m of them if you have m parameters. For the Hessian, there's m squared. Again, if you have 1,000 or tens of thousands of parameters, you've got to square that to write down the Hessian, and then it takes cubic time to actually compute the inverse of the Hessian that you need. So it's very expensive. People have almost solved that, though, in practice, because there's methods like LBFGS, which is an efficient high-dimensional Newton iteration for convex sets. So instead of computing the full-dimensional Hessian, they compute a low-dimensional approximation and then a low-dimensional inverse approximation. And so the complexity shrinks, and it's now, instead of the full rank, it's in terms of k. And it is true that for a lot of problems, even though there's m dimensions for the full parameterization, there's k dimensions which capture the most rapid change in the function, so it's sufficient to consider that subset. But we'll probably have instability problems. LBFGS helps a bit with that, but whereas the stochastic gradient is nice and stable because we're only computing gradients and it's an unbiased estimate, It has some variance, but not a massive amount of variance. With Newton's method, we're always doing inverses of this curvature matrix, and that makes it typically less stable, especially when you're estimating things from a subset of data from a mini batch. And we already zeroed in on the main problem, which is it does the worst possible thing when it's near a saddle point. So there have been fixes to this. There are pseudo-Newton methods that force the curvatures to be positive in the, let me think. Yeah, they force the curvatures to be positive, which prevents you from going to the optimum. So this is still a somewhat active field of research, but it really hasn't demonstrated big performance gains for most problems. So people still use SGD most of the time. Okay. Okay, so here's an animation of some of the methods. Well, so SGD is the red one. Let's go back. So if you can this time track the red curve. So you can see compared to some of the other points, and the optimum's off up and to the right, you can see that SGD, it's good in the sense that it's not wasting effort. It's creeping along because it's directly using gradient, and the gradient gets pretty small as you get close to the optimum. It's getting very flat, meaning the contour lines are spaced wide apart. And so it's slower than the other methods that we're going to talk about. But still quite reliable. I mean, it really is zooming in quite efficiently. And if you notice, because this version's tuned to take very small steps as well, you notice that it's most of the time going at right angles to the contour directions. Actually, I guess that's kind of obvious. Okay. So we said already that the actual gradient direction is not the best direction to move in. That would be the Newton direction. So if we take steps that are too large, you can probably guess that it's going to tend to oscillate. And you can imagine this visually. If you had an ellipsoidal bowl and you let go of a ball in that bowl, it's mostly going to rock back and forth across the bowl rather than going down. So he's back. All right. So this time we're going to use Newton's first law from physics, which is that bodies in motion tend to stay in motion. So if you like, objects have memory of motion. And it can be expressed quantitatively as force equals mass times acceleration. So yeah, so in the context of SGD, the method that we use is typically called SGD with momentum, but the actually more important part is that it's SGD with momentum and damping. So there's a damping force introduced. And damping, it's also known as viscosity. So it's a force that's proportional to the velocity of the object and in the other direction. So if it's kind of a drag, and it's taking energy out of the system, which is how the particle can converge. Otherwise, it just would keep, if it's got potential energy in a bowl, it's just going to keep oscillating back and forth. So SGD is, we introduce both, we make it a second order system, we introduce both momentum and drag. Okay. Now, in the toolkits, you'll see a constant, a hyperparameter called momentum. And just to be clear, that's not really, it's not even clear what that would mean, because momentum is not some kind of scalar in a dynamical system. What it really is derived from the damping ratio, or the damping constant. Okay, so let's look at the formula a little bit more detail. So if we just had a physical system, then the force is mass times acceleration, which you can write as mass times the derivative of velocity with respect to time. So if we do have a damping term, which is the velocity-dependent force in the opposite direction of the velocity, often the constant for that is nu. I know that's confusing. It's nu times v, but the nu is the pointy one. So now the force over here is, so we're assuming the force is being applied by the gradient of a loss function. So we're trying to push it in the gradient direction. This is the viscous damping, though, which is going to slow it down in proportion to how fast it's moving. And that is actually stabilizing it. That allows it to eventually stop. And then the right-hand side is just mass times acceleration again. And just to make it a full second-order system, we need one more equation, which is the trivial one that the position derivative with respect to time is velocity. Okay? This is familiar from physics or somewhere, if you didn't do physics. All right. Now we do a thing that numerical analysts probably would hate, but we turn those differentials into small steps. And so we say that the step in velocity, just basically rearranging the upper left formula. So we just shuffle this around to get dv by itself. And then it's dt over m times this expression here. Okay? So, yeah, so that's how much the velocity should change in each time step. And if we want to write it as a complete update for velocity and position, then the new velocity, after we do an update, is the old velocity times 1, because we're adding dv to v to get v prime. Just to be clear, v prime is not a derivative. It's just the value after doing the update. So it's the old v plus this change, this dv, which is this thing over here. And yeah, that's the term over there. And I realize I missed, okay, sorry, so there should be a viscosity term in here. Sorry about that. I'll fix that. Anyway, the point is that this thing here is a constant that's less than 1. It's derived from the time step, the mass, and the constant nu. So, and hopefully it's somewhat intuitive that let's just turn the force, the gradient off. Imagine there's no slope. Then if you keep iterating v, where you're multiplying the old value by a constant less than 1, it's just going to decay down to 0. All right, so momentum plus damping will cause the particle to slow down and stop eventually. But the effect of the momentum, because it does remember the old velocity, it will generally prevent it from oscillating back and forth, because when you accumulate, effectively you're accumulating your history of gradients from the past, and that tends to convert that oscillation into a steady progress in the right direction. So I hope that's sort of intuitive. So this is basically a moving average now, a common value for this constant. I'll put it on the next slide. So we typically hide that derivation and just simplify the equations to something like this. We call it a momentum. You can call it velocity. If the mass is not explicit, it doesn't really matter. Anyway, so the new momentum value is the old momentum value times a constant mu, which is less than 1, plus the gradient contribution. All right, so now we have these two simplified equations. P is kind of now a moving average, if you like, of the gradient, actually, and the negative gradient. Alpha is the learning rate, as before. And the weight update is just adding, weights are like x. So we now update, add the new update of momentum to the weights to get the new weights. So this is the standard formula for an SGD with momentum. So we're clear on this so far? But it's useful to just keep in mind that mu would be exactly 1 if there was no viscosity. From the previous equation, I won't put it up again, but it's 1 minus dt over m times the viscosity. So it would be exactly 1, which means the algorithm wouldn't work. It would just oscillate everywhere. So it is critical to have some viscosity in the system. And the bigger the viscosity, the further the mu constant is away from 1. So like I said, 0.9 is a common value. Sometimes it's a bit bigger or smaller. All right, so now we can visualize again a comparison between SGD and red, and which one is momentum is green. So you can see momentum plus viscosity is overshooting because it's accumulating gradients from the past. Whereas SGD, once you get to this position here, the gradients are now pointing across. They're not pointing down anymore. But because the green trajectory has momentum, it's remembered the gradients from back here, which do point down, and therefore it overshoots. And it gets to the flat part and comes back, and it comes back a bit quicker this time than some of the other, or at least than the SGD, because it's able to remember, even though the gradients in the lower part of the curve, or of the surface, excuse me, they're very small, but still, because it's able to accumulate them with a moving average, it goes a bit faster than it would otherwise. And in the graph below, you can compare regular SGD and the green, maybe not super easy to see, but the green curve is in here mixed with the others, so it gets to close to the final loss much more quickly than the SGD does. Okay, any questions? All right, so SGD versus SGD with momentum and damping. So there's a subtle point in the momentum update which can make a big difference. Well, it makes a huge difference for convex problems, and it even makes a bit of a difference for non-convex optimization, which is the formula that we wrote down. Here it is again. This is the SGD with momentum and damping. If you look at it graphically below, you start at a red point in the parameter space, compute the gradient direction, the red arrow. You take a step. All right, you compute your actual step, which is in blue, which is the P update, as a sum of the momentum step, which is just the constant less than 1 times the previous momentum. You multiply that by something, and then your gradient step, computed at the red point, and add them together to make the actual step. So that's reasonable, but you could ask the question, is that as accurate as I could really be? Because now I kind of know I'm going to take the momentum step, right? Because the momentum step uses a value that I obtained in a previous iteration. So you can ask the question, would it be better to compute the gradient at the red point where I currently am, or take a partial step towards the final? So in other words, take the partial step with the momentum first, and then recompute the gradient. That's very intuitive because, well, hopefully it's intuitive. That momentum step that vector should actually be pretty close to the gradient vector, because the green vector is a moving average of gradient vectors. So, and assuming the current gradient is close to the previous gradients, both of those are going to be fairly close to each other. So if I first take the momentum step and then do the gradient, I've actually gotten a lot closer to my eventual point, and so the gradient estimate probably will be more accurate. So that's what Nesterov does. So it's called Nesterov's accelerated gradient. And the idea is basically you take the momentum step first and compute the gradient at that point instead of the starting point. And in case it's different, generally the momentum step takes you quite a lot closer to the final blue arrow, and intuitively you would expect that to be more accurate. All right, and computationally it looks like this. Now you've got to, basically add mu times p. That's the momentum step. You add that to the weights before you compute the gradient. In other words, the formula is the same. So is that clear? All we modified is the term in purple, and it's nothing more than changing the weights before you do the update. Okay. All right, so it's a simple trick, and surprisingly, though it changes the asymptotic convergence of this method on convex problems by a lot. So whereas normal SGD on a convex problem converges at something like 1 over t. So that's the error, or the gap between the current loss and the final loss decreases as order 1 over t. So that's fairly slow decay, right? T is the number of steps that you've done. Nesterov, on the other hand, has this. This is not called quadratic convergence, by the way, even though it's an inverse quadratic. But still, it's much faster. So after 100 steps, you expect the error in the loss to be 1 over 10,000, so much better than 1 over 100. So it's very interesting. And there's been a lot of work more recently on even better versions of accelerated gradient. But anyway, there's a simple idea. It's the sort of idea of exactly where should you take the gradient. Okay. So back to the simulation of different methods. The Nesterov method is usually abbreviated as NAG, which stands for Nesterov Accelerated Gradient. So SGD is the one in red that's going slowly. The regular momentum is green. And yeah, it's a little hard to see on the bottom, but hopefully you can see the purple and green compared to each other. Nesterov doesn't overshoot as much, and it gets into the to the center quicker. And it's overshooting less because if you think about it, it's using the gradients a little bit further ahead. So as it goes down and passes that star, it's already getting gradients from below, which are pushing it back. So it goes a little faster. Okay, so let's just pause there and make sure we're all on board. So the next set of methods are going to address a different challenge with stochastic gradient, which is the fact that the contours in general are not circular, right? You'll often get some ellipsoid. You'll inevitably get an ellipsoid. The ellipsoid just means that the curvatures are different in different directions. And though, as I mentioned earlier, if you instead somehow had a spherical contour map or a spherical surface, second order surface, even the simple gradient goes in the right direction there. So what RMS prop and the other methods do is some kind of coordinate scaling to make the attractor as close as possible to a sphere. So anyway, so if we define this quantity S, S is some moving average with itself again. So beta is another constant that's between 0 and 1. And so when you do beta times the previous S and 1 minus beta times this quantity here, which is the squared gradient, what you're estimating is a moving average again, an exponential moving average. Do people know what I'm saying when I say exponential moving average? I guess I'm defining it. It's a, if I define ST in terms of beta times ST minus 1, if you apply that recursively, it's going to be beta squared times ST minus 2 plus beta cubed times ST minus 3, etc. So you can see that's kind of an exponentially weighted sum of the previous S values. So it's sort of a long-term window of history of S. And each step, I'm adding in an estimate of the squared gradient at that step. Yeah, and by this I mean actually, well, it's possible to define this a couple of different ways, but the simplest way is for this to be the element-wise squared gradient. So ST, in fact, has the same dimension as the gradient. Is that clear? So S is actually a vector, and when I write G at time t squared, I actually mean take each coordinate of G and square it to make a vector of the same length. Okay. Now the update looks like this. And again, for the division here, it's still element-wise. So the gradient has some dimension m, and S has dimension m, and when I say square root, I mean the square root of each element, element-wise. So you could do everything independently on each coordinate, actually. You could just compute, if you want to think of it that way, if it's easier, just take the gradient coordinate by coordinate, the corresponding weight vector of that coordinate, and apply this to the scalars, because the estimates for different coordinates are actually independent. But what it's done is now normalize the gradient of each coordinate so that it's basically its expected, well, its variance, if you like, is 1 now. So the expected squared value, it's not quite variance, I shouldn't say that. It's the expected squared value of the gradient in each coordinate after this normalization is 1. So would that make, does that make one of those ellipsoidal attractors circular or spherical? And the answer could be yes, no, or sometimes. So the right answer is sometimes. Yeah, so we'll see the plot again in a moment. But eta grad is a variation of RMS prop, which instead of computing a moving average, actually computes a cumulative sum of the squared gradients element-wise. All right, so it has an update that looks like this. It's very similar to RMS prop. But this one, eta grad, interestingly, has a built-in effective learning rate decay. Because this sum here is cumulative, if you assume for a moment that the gradients don't change much over time, then the size of this sum here is proportional to t. Okay? So the magnitude of c is growing in proportion to t in each coordinate, which means the square root is growing proportional to square root of t. Yeah?
Does that mean that RMS prop is relatively less resistant to exploding gradients depending on what your beta parameter is?
Compared to
eta grad.
Oh, compared to this one. But both of them are very similar. The probably RMS prop, yeah, would do a little bit better because the exploding gradient, because it's an exponential moving average, the relative contribution of the gradient in the same step to that moving average is bigger than this one. Here, because it's a long-term average. But it's, well, it's a complicated question. I think I will punt that one a little bit. There isn't a clear better in that situation. For exploding gradients, there's other tricks too that people use. You can also just clip the gradient. That's commonly done if they're a problem. There's another related problem that I'll get to in a moment with another method called atom. So, yeah, but both methods have some risks with exploding gradients, so there's not a clear priority. Yeah, so both methods, because they're effectively trying to scale gradients, they work well on data sets where there is a big range of gradient magnitudes in different directions, or if you want to think about it, where the minima have a very elongated ellipsoidal shape. Yes, so a data set type in which we can quantify that is text data. Text data is commonly uses parameters that are indexed by the word. And words in English and most other languages satisfy a power law distribution for frequency. So the frequency of the jth most common word in English is about 1 over j. It's not about 1 over j, it's proportional to 1 over j, and the constant is something like log of 100,000 or something like that. 1 over the log of 100,000. So anyway, because the word frequencies, because there are maybe 10 to 100,000 words in fairly common use, the frequency of those words varies by about 5 orders of magnitude. And sooner or later, the effect of those on the parameters is also proportional. We're hand-waving a bit now, but there's a similar variation in the scale of the minima. So depending which direction you are. So using RMS prop and AdaGrad will tend to normalize those effects and bring those gradients into the same range. So RMS prop and AdaGrad are almost required if you're dealing with text data. Okay. With more complicated feature dependencies, it doesn't work as well. So the answer that I was asking for before, what does AdaGrad and RMS prop do to an ellipsoidal surface? The answer is if the variation in curvature is aligned with the axes. In other words, if it's like the picture I drew earlier where it's longer in x and shorter in y, these methods would scale x and y such that it's circular. On the other hand, if it was an ellipsoid that had dependencies between the two weight parameters, and say the ellipsoid was at 45 degrees, then it's not going to help, right? Because scaling x and y when the ellipsoid is at 45 degrees doesn't change things. So it works best when you have sort of differences in dependence on the parameters, but aligned with the parameters. Okay. RMS prop is a heuristic method. AdaGrad is a method with some bounds. And RMS prop by default has a fixed learning rate, and that's suitable for long-term training. AdaGrad decays the learning rate, as we argued, by 1 over square root of t. And that works for some problems, typically small networks. But it's probably too fast. In other words, it gets to be too small if you want to run for a long time. So on the plot again, AdaGrad is in blue, and RMS prop is black, I guess. So if you can zoom in on the blue and black, they're both coming from above because they don't have momentum, so they don't overshoot. And there's some small differences in performance. You can see, hopefully, AdaGrad is slowing down and it's slower than RMS prop because it doesn't have a fixed learning rate throughout the process. Okay. All right, so another method that's widely used, well, it seems kind of common sense. Why not combine momentum with coordinate scaling? And in fact, that was done. And there's a method called ADAM, which actually combines momentum, coordinate scaling, and bias correction, what they call bias correction. 2 out of 3 of those are really good. The other one, they kind of messed up. So it's a bit unfortunate, but the implementations of this they work very well or they work very badly, and I'll explain why. Okay, so the methods that we saw so far are actually quite similar. At least RMS prop and momentum are similar in the sense that they compute moving averages of two things. So for the momentum method, you're computing a moving average of momentum, right? Which is basically, yeah, it's a moving average of the gradient. The S parameter for RMS prop, that coordinate normalizing parameter, is a moving average of the squared gradient, squared coordinate-wise. So, you know, you can just compute both of those. They're both estimates of moments, actually, where a moment is a, you know, like an estimate of a quantity or its powers. And then the new update, which would now have both momentum and coordinate scaling, would look like this. So there's the momentum estimate, and there's the coordinate scaling estimate, again with the square root. So that's a really good idea. It works pretty well. Any questions about that? So far we just combined RMS prop with momentum. It's a very natural thing to do. The only caveat with this so far is that the optimum time scales for these moving averages are quite different. And I mentioned before that for momentum, it's common to use a moving average of about 0.9, which means that the effective width of the moving average is about 10 steps. This one, it's commonly, the moving average of the squared gradients is usually much bigger, because the idea is that the magnitude of the gradients tends to vary much more slowly. And you want, though, because you're going to use this in a denominator, there's a danger of it exploding if your estimate is too small. So a safer thing to do is use a much longer estimate for the S parameter. And so that beta 2 is commonly 0.999 or 0.9999. So in other words, the window is 1,000 to 10,000 steps. So it means that this thing, if you initialize the moving average to 0, it means that this one grows quickly, whereas this one is growing much more slowly. And that's a danger, right? If this, after 10 steps, this is basically its full magnitude, but this takes 10,000 steps to ramp up. So that's a danger. There are a couple of ways they could have fixed that. What they chose to do is they call bias correction, which unfortunately is probably worse than not doing bias correction. Yeah, it's all right. So here you go. Here are typical values for beta 1 and beta 2. Bias correction, yes. What they mean is that these estimates are biased relative to an exact moving average over time. However, the bias estimate assumes that the thing being estimated is constant, and that's not a bad estimate, a bad idea for the numerator, the S squared. The gradient squared estimator, but it's a terrible idea for the numerator, which is this thing. Because if you remember the pictures we saw before where the gradient itself is oscillating, the squared gradient's about the same in those oscillating situations, but the gradient itself is actually reversing. So it's very far from constant. And anyway, this is the bias correction. It's basically the formula for a geometric series. And it basically says, if you assume the thing you're estimating, either the gradient or the squared gradient, assume that's constant, then if you only have a few observations, you can estimate the final value by computing this formula here. So it's basically the correction for a geometric series. If you have two values, you multiply in the numerator by 1 minus 0.9 squared. So that's not too bad. It's like 5 5 times p. This one is a bit more alarming. If you on the first step, this is 0.9999, so this is 1 over 0.0001, so this is 10,000 times the first estimate. Anyway, so it's actually not terrible to do it for the denominator, because instead of having an estimate that was too small without the bias correction, if you overestimate the denominator, you just end up with a value that's too small. It's a lot safer than a value that's too big. And you can add epsilon to divide by 0. But anyway, the bias correction is based on the being constant. It does work great sometimes, but often it fails as well. And the trouble is that this correction is okay, the denominator, because it's going to tend to overestimate, or at least it'll have a noisy estimate, but that's not too bad because you're dividing by that quantity. But the other one is terrible because the gradient itself is often oscillating. So adding a correction that assumes that it's constant is terrible. So if you're lucky enough to have an implementation that lets you turn off that bias correction on the numerator and not the denominator, you should use it. I just don't know if that exists. But so anyway, it's worth trying Atom, but it has this kind of weakness. Anyway. Right. Okay. So let's see what we can get done. These are typical loss curves over time for different learning rates. And okay, so if you have a choice of learning rate, what should you use? It's not obvious. You have high, low, and good. What do you think you should choose? So high learning rate goes nice and fast, but then actually saturates, which is interesting. And that's because with stochastic gradient, you're taking random steps. It's kind of like trying to, having a ball settle in a bowl where the ball is shaking violently. It's, the oscillation in energy keeps it from actually finding the lowest point in the bowl. So let's try again. Low learning rate, if this was a convex problem, low learning rate would just be slow, right? It would eventually get to the optimum. But interestingly for deep networks, low learning rates often don't get you to a good optimum because they lack enough energy at the beginning. They often actually settle into a bad optimum, especially for things like transformer networks. You've really got to tune the learning rate to be high enough at the beginning, or they settle into very suboptimum final solutions. So low learning rate is not just slow, it often doesn't get you to a good final solution. So good learning rate, well, we didn't really define that. It's presumably higher than the low learning rate and lower than the high learning rate. And it can be good, but it's trying to make a trade-off in two different parts of this cycle. So you want high learning rate first. You can see that's better. And then you want low learning rate later on to allow the thing to settle. So in fact, neither of those, or those three are not really optimum. Usually you want a decreasing learning rate to get the best outcome. All right, and here are some common learning rate decay functions. You can step by some fixed ratio every number of epochs. The eta grad delay 1 over t square root of t is shown last. Sometimes people use 1 over t. That's typically for very aggressive convex problems. And exponential decay is kind of it's a smoother version of step decay. So here's the learning curves for the ImageNet optimization task on an actual sort of standard ImageNet. It's called AlexNet. And you can see that the learning rate alpha stepped in orders of magnitude after about 20 epochs. And you can see it, let's just worry about validation accuracy. It already really saturated at about 40% here. And simply reducing the learning rate So it wasn't going to get any better than that, most likely. But dropping the learning rate by an order of magnitude lets it go way up to nearly 60%. And then dropping it again, it gets a little better, up to 62%. So that's very commonly done with vision-based networks. The other thing that's important is that the accuracy is very sensitive to L2 regularization because it's really an over-parameterized model. And here the best value in red is right between these two other values. It's fairly narrow range. If you under-regularize, this thing kind of overfits and ends up with really bad accuracy. If you regularize too aggressively, this is the weight on the weight decay, which is equivalent to adding an L2 term on the weights to the final loss. If you regularize too much, you also drop the accuracy a lot. So L2 regularization is a problem. Last topic, really. So people were worried about local minima as well as saddle points. Saddle points slow you down, but they don't trap you, whereas local minima will trap you. Interestingly, though, people have found that for over-parameterized models, even though they have local minima, the more parameters you have, the closer the optima get to the optimum. So the number of parameters here is increasing from the yellow to the red example. And the histogram shows the count of optimization runs where the optimization run achieved a particular loss. So it's a scatter plot of loss across entire different runs. So they did a lot of runs. And you can see that for the higher dimensional model, every simulation got in that histogram of red curves. And a lot better than the less degrees of freedom model. It's actually the number of hidden layers in one layer of this model. So so you can see that the histograms, as you go from a few hidden units to many hidden units, they're both getting narrower and also improving. And that's a general trend. So let me just wrap up here. So and there's some more details in the slides of exactly what problem that was. And just a summary of deep learning. So people have moved from focus on local minima to focus on saddle points, and over-parameterization actually helps. And here's a quick summary of what we did. So don't forget to get assignment, keep making progress on assignment 1. It's due in a few weeks.